So let's use these harmonious intervals to explore another way to construct a scale. Two notes sounding in perfect unison is the most harmonious. An octave apart, the fundamental and the second harmonic, is the next harmonious. And the fundamental and the third harmonic, with a ratio of 3 to 2, is the next harmonious. An interval where the ratio between frequencies is 3/2 is called a perfect fifth, although that naming, much like the octave, will only make sense later. So we'll start with a fundamental of 260 Hz again, and multiply by 3/2 to obtain a second tone, 390 Hz. Then we'll multiply that frequency by 3/2, and rescale, so that we get a frequency between 260 and 520 Hz. Then we'll multiply that third frequency by 3/2, rescale if necessary, and so on. If we do this 4 times, we get these tones in order. This probably sounds familiar. It's what's now called the major pentatonic scale, and it's absolutely one of the most common scales. So many nursery rhymes, folk songs, pop songs have melodies that involve only the pentatonic scale. Let's keep going to obtain a couple more distinct tones. When we sound them in order, we get this. Now that's not the major scale, although it's close. For those of you who know some music theory, this is called a Lydian scale because of the raised fourth. We can keep going. We can keep going until, well, how will we know when to stop? Will we ever, by stacking fifths, that is, successively multiplying by 3/2, wind up some perfect octave up from the fundamental? Another way of asking that question is, can 3/2 raised to some power ever equal 2 raised to some other power? Well, we'll suppose that it is possible, and then we'll deduce from that something that is absolutely absurd, and that will show that there's no way that it can be possible. So suppose that there are some integers k and m such that 3/2 to the power of k is equal to 2 to the power of m. If we rearrange this equation, we wind up getting that 3 to the power of k is 2 to the power of m plus k. But any power of 2 is going to be even, and any power of 3 is going to be odd. This is clearly absurd, so there cannot possibly be such integers. In the current context, that means that stacking fifths will never land us back at the fundamental. So our process of stacking fifths could go on indefinitely. But let's perform this procedure, 12 times, recording everything on one page. The rescaled powers of 3/2, the decimal approximations, and the frequencies that result when you apply these to a base frequency of 260. Now this last ratio, 3 to the power of 12 divided by 2 to the power of 19, is really close to 1. And the frequency that results, if you apply it to a fundamental of 260, is close to 260. In modern terms, they differ by about 23 cents, which is certainly perceptible. This interval of 23 cents is called a Pythagorean comma. Because we've almost but not quite come full circle, any iterations of our procedure from this point on will produce tones which are quite close to tones we've already obtained. This is one explanation for why the chromatic scale now has 12 notes. Let's adjust our procedure just a little. Instead of only going up from a fundamental, let's also go down. By going up, we'll obtain tones that we already have, but by going down, we'll get some new tones. To go down from a fundamental of, say, 260 Hz, we need a frequency f such that the ratio of 260 to f is 3 to 2. In other words, f is 2/3 times 260. So going down by fifths amounts to multiplying by 2/3. So if we start with a fundamental and multiply by 2/3, then multiply that pitch by 2/3 repeatedly, rescaling as necessary. Actually, what we're doing there is we're rescaling, multiplying by 2, so that our factor is between 1 and 2. We're only ever multiplying a pitch by some number between 1 and 2. Well, if we take these fractions, 2 to the power of something divided by 3 to the power of something, and write them with their exponents, we'll write them like this. I'll also record what those exponents are expanded out here in purple. And in a third column, I'll write out the decimal approximations. Now these are sorted. These are after you've gone through the process, you've obtained 12 tones, and then you've sorted them in order. Now if we do the same thing for stacking fifths up and record the same kind of table, so powers of 3 over powers of 2, those powers expanded, and then the decimal approximation, we'll have these two lists of all the factors between 1 and 2 that we get by going down in fifths or up in fifths. and we see that the two lists of numbers are really similar. Look at the decimal approximations. So we have a choice to make. What we're going to do is we're going to rely on the idea gleaned from the harmonic series that ratios with smaller denominators, fractions with smaller denominators, give more pleasing, harmonious intervals. The story is a little bit more complicated than that, but let's roll with that to build a scale. So what we'll do is we'll select the fraction with the smaller denominator. So here we have, including the fundamental, of course, a scale made up of 12 tones obtained either by stacking fifths up or stacking fifths down. We've selected the ratios with the smallest denominators, and we've only used fifths, one of the most harmonious intervals, to construct this scale. This is called Pythagorean tuning, and it dominated Western music for centuries. It's also called three-limit tuning because every pitch is obtained from the fundamental by multiplying only by powers of 2 or 3. Here's a virtual piano that's tuned according to Pythagorean tuning. The fifths all sound really nice. Oh wait, except for maybe that one. The ratio of these two pitches you can calculate to be about 1.44, which is quite far from 1.5. No matter how you tune a piano according to Pythagorean tuning, you're always going to have one of these so-called wolf fifths. There's just no way around it. This Pythagorean tuning is great if you stick with a particular key and if your movements are mostly fourths and fifths, and as long as you avoid the wolf intervals. The major third in Pythagorean tuning, with a ratio of 81 to 64, is close but noticeably sharper than the ratio 5/4 that appears in the harmonic series. So for years, composers using Pythagorean tuning shied away from this less harmonious interval. It sounded jarring and sharp. The intervals of the fifth, fourth, and octave reigned supreme through most of the Middle Ages. Here's an interval of a major third in Pythagorean tuning, and here's an interval of a major third with tuning according to the harmonic series. It's worth mentioning that the ratio between the major third obtained from Pythagorean tuning and the major third obtained from the harmonic series is 81/80, about 22 cents, which is called a syntonic comma. But maybe there's a way to refine our pitches to include the ratio of 5/4 that occurs very early in the harmonic series. Here's one way. If stacking 4 fifths results in the ratio 81 to 64, which is a bit sharp, in particular a syntonic comma sharp, than the ratio 5/4, what if we shave off a little bit from each of those perfect fifths? That is, we temper each fifth by 1/4 of a syntonic comma, or about 5.4 cents. Then stacking 4 of these will give a ratio of 5/4, or extremely close to it. This method of tuning was called mean tone temperament, and it rose to prominence in Western music in the 16th century. Remember how the threshold of differentiation of pitch for most people seems to be around 5 cents? Mean tone temperament compromises the fifths by about 5 cents for the benefit of the thirds. Instruments tuned with mean tone temperament could really allow composers to incorporate intervals of a major third into their work. These small changes, even if they seem trifling and insignificant, can really have a huge impact on creative output. Allowing the interval of a major third, or the ratio 5/4, to appear in your scale really gives rise to a whole array of sophisticated harmonic ideas. Now, so far we've been privileging the octave and the ratio 3/2, or the interval of a fifth. But if we want the interval of a major third, or the ratio 5/4, to appear in our scale, rather than starting with only fifths and adjusting them, as in mean tone temperament, why not just throw the thirds right in there from the get-go? Stack major thirds, or intervals of 5/4, and intervals of a fifth, ratio 3/2. If you do this, you get something called 5-limit tuning, because any frequency you obtain in this way by stacking fifths and thirds will be expressible in terms of powers of 2, 3, or 5. Now you could keep going. Why not 7-limit tuning? Include the ratio 7/4, which appears relatively early in the harmonic series. 11-limit tuning, 13-limit tuning. You could go on. When you do this, you get a little bit more flexibility. you also might get some intervals which maybe don't sound so harmonious because you're moving a little further out in the harmonic series to do so. But no matter how you do this, you're never going to completely avoid the issue of Wolf intervals, which we saw with Pythagorean tuning. At some point, you're going to encounter two pitches in your scale, where the ratio between those pitches is pretty close to an interval, a ratio which appears early in the harmonic series, but it's not quite, and so it sounds a little bit out of tune. Mathematically, the way this plays out is, for example, you can't express powers of 5 in terms of powers of 2 and 3. 5 is prime. You can't express powers of 3 in terms of powers of 7 and 5. You can't express powers of 11 in terms of powers of 2, 3, 5, or 7. So these issues don't have to be a big deal. If you have an instrument tuned in such a way, and you only play music on that instrument that avoids those Wolf intervals, no big deal. Or if you have an instrument such as a trombone or a fretless instrument like a violin or a cello, which can produce microtones, or even the voice, and you have a skilled performer who can adjust their intonation on the fly, either raising the pitch a little bit or lowering it just a little bit so the intervals sound really in tune, that is more aligned with their harmonic series, that can be fine as well. Barbershop quartets do this all the time, and string quartets. But if you want a statically tuned instrument that's really flexible and versatile and allows switching between keys on the fly, then some compromise has to be made. Using these simple intervals from the harmonic series is not going to be enough.